In this video, we will compute a new approximation to number pi using this series. Note that this series is different from the one that we have used in the previous exercises in this academic year. And the novelty here is that we have to compute this using a Matlab function, okay? And instead of prescribing the number of terms as we did in exercise 2, now we will prescribe a given value of the relative error. So what we have to do is to start our Matlab session. First, set our current folder, and I will create a new folder called problem 3, and I open it. So what I suggest is to start with writing the function. So the first sentence will be function, and we have to add the declaration of the function. So it will be compute pi rel error, where the input parameter is the prescribed relative error and the output parameter is the approximation to number pi that will be called p. Okay, so what we have to do is to set an initial value to the summation. That means to set an initial value to compute this summation here, then set an initial value for the counter I that takes into account the number of terms that we are adding. So that will be, for instance, sum equals 0, and then I equals 1. Okay, and then we will write the while structures, which is while a condition is true, repeat the sentences that are inside the while structure. And the basic idea and the thing that we have to take into account is the condition, which will be the condition, okay? And the condition will be something like the relative error, the current relative error, bigger than the prescribed relative error. So the idea is we have to loop while the relative error, the current relative error, is bigger than the prescribed one. Okay. Now, what we have to ensure is that we will go into the loop at least once. So what we will say is that the initial value of the relative error is, for instance, infinity. Well, it's not infinity. Inf is a keyword in Matlab that is assigned, or it's a variable that is assigned to the maximum number that can be stored in Matlab. So this is the maximum number that we can store, and it will be, by sure, bigger than the prescribed relative error. This is the first thing. So now we ensure that we will go inside the loop. So inside the loop, we have to do at least 3 things. The first one is to compute the approximation. Okay. The second one is to compute the relative error in order to check in the next iteration if you have to add a term or not. And the third is to update the value of the number of terms that we are adding. So we will start by the first thing, to compute the new approximation, and that will be like something like, first we will compute the value of the term that we have to add, so that will be 1.0 divided by something, and this something is the product of 2 times I plus 1 and to the power of 2, so I compute the product of this quantity by itself, times the same, but now, sorry, here dot 1 and dot, okay, 1 is real number, and the same quantity, but now with a minus instead of a plus. This is the value of the new term. Okay, we got a semicolon here. So it is 1 divided by 2 times I plus 1 to the square times 2 times I minus 1 to the square. So the new value of the summation will be the previous value plus this term. And the current approximation to pi approx, will be, according to the expression, the square root of 16 times the summation plus 8. So that will be the square root of 16 times the summation plus 8. Okay, so this is the new value of approximation, and the value of the relative error of the current approximation will be the absolute value of the absolute error, which will be, not that the approximation to pi, it's called p, so here we have to use p, and then the absolute value the absolute error will be p minus pi divided by the exact value of pi, which is pi. So this will be the relative error, and then we only have to update the value of the counter of the number of terms. So if in addition we want to write some information in the command window about the current approximation to the number pi, what we can use is the function, the fprintf sentence that allows us to write something into the screen with a prescribed format, and the first argument is the format, and the second one the list of variables that we want to write, which are the current approximation and the current term, the current number of terms, the current approximation to pi, and the current relative error, so will be rel error. And now we have to add the format, and the format is, for instance, the number of terms, so it's the term that we want to write, and this will be decimal number of maximum 4 digits. Then will be the approximation, and that will be, for instance, 20 digits with 12 digits for the decimal part, and using an exponential form. And then the relative error, and that we will write with the same format, that it's 20 digits with 12 digits for the decimal part in exponential notation. And then the new line format. We want to write this, maybe what we have to do is to split this sentence into lines, okay? And now we have our function. We have the final version of our function, so we can save it. And Matlab suggests the name for the file should be equal to the name to the function. Okay, we save it and we have the file there. And now we will write the main script that will call the function. So the first sentence in the script will be clear and CLC to clear the workspace and the command window. Then we will use the input parameter to ask for the prescribed error. So we will say prescribed error equals input, and then, for instance, enter the prescribed error. And once we get that, I forgot to close the string, and now we can call the function. Okay, the function will be, the calling sentence will be, for instance, the approx to pi equals, and now here we have to write as input parameter the current prescribed error. So we can run now the code. The name of the file will be problem3, and Matlab asks for the prescribed error. If we want to get 3 significant digits, we have to write .5 e minus 3, and we have an error in the f prime f, and this is in line number 13 of the sentence, and it says that f print f, we need to add here a t. Okay, we save this modification and we run again the code, and then the error should be .5 e minus 3, .5, excuse me, and we get that with 3 terms in the series, we get an approximation with 3 significant digits. If we run again it and ask for a higher number of significant digits, we can say, for instance, .5 e to the minus 8 to ask for 8 significant digits, and with 150 terms in the series, we got this approximation. Note that the error is smaller than .5 for times e 10 to the minus 8. We can even increase the number of significant digits. For instance, .5 e to the minus 10. So this is 10 significant digits, and we need 696 terms in the series to get this approximation. So, as you can see, using a number of terms in the series smaller than the one that we required in the previous exercise, we get a nice approximation to the number pi. That's all. Thank you very much for your attention, and see you soon.